As a way of wrapping up the conversation and the introduction of computer organization and microprocessor, I thought it would be a good idea to talk about a little bit of the history. As we've talked about in the past, in previous videos, transistors are really the foundation of everything that's happening in the computer world, and the reason we have made as much of the advances that we have made. And really has to do with a phenomenon, and that phenomenon is the ability to produce these transistors. So before I go too far, transistors are, you can think about as a electronically controlled switches. That's all a transistor is. It's either open or closed, and you can turn it on and turn it off electronically. And the big reason why we have so much functionality in our computer system, we can do so many things with it, because over the last roughly 80 years or so, from the time we built the first electronic transistors in the form of a vacuum tube, we've been able to reduce the size and the cost of these dramatically. And I'm going to spend a little bit of time talking about Moore's law in a minute, and kind of what Gordon Moore, who is one of the founders of Intel and used to work in Fairchild and all of that, and one of the basic driving forces in Silicon Valley around IC development and chip development, had this projection which basically said transistors per number of transistor per square inch will double every 18 to 20 months. And this has been true for the last 67 years, even though every decade or so somebody will come up and say there's no way we can go further. As a matter of fact, right now we have a large number of people say that cannot continue on into the future. But I'll show you some trends which basically says they are indeed growing at that rate. We have been able, by innovation and creativity, people have been able to continue that growth. And this is a geometric growth, which means once you look at the numbers, you'll see some amazing things happening. As just a starting place, let me walk back and let's take a look at what if you've never seen a vacuum tube, maybe talk briefly about what a vacuum. These are pictures of a vacuum tube. If you want to look at them, here is the most recent one. This is probably vintage 1950s, 1960s. This is probably vintage 1920, 1930s. Even at the smallest form, it used to be about an inch in diameter, about 3 inches tall. So you can imagine if you needed 1,000 transistors, you had to have 1,000 light bulbs that were relatively unreliable, such that they would last for 1,000 hours or so. So if you had like 4K system, 4 kilobyte bit system, you would have 4,000 of these in your system. With them lasting 1,000 hours each, that means every 15 minutes one would go out and your computer would stop working. Pretty inconvenient. And they were expensive. They were many dollars per unit. Now, if you take a look at some of the trends that we have, this one doesn't go completely to 19. To 19. Let me see if I can get this to a place where you can see it a little better. So if you look at it, it starts around 1971, around 4,000 or around 2,000 transistors or so. It varies depending on what you look at it. In the 1980s, around 10,000 transistors per chip. And if you look at it now, actually this is not even now, this is in the 2011 time frame, about 7 years ago, you could get 2.6 billion transistors. So let's just take a minute and kind of make sure we understand this one. So in the 1940s, 1950s, if you wanted a single switch, you would get something that had basically a diameter of about 1 inch and a height of approximately 3 inches, and cost multiple dollars, let's say $5 to $10. Okay. Now what's happening in the, let's say, 1980s, you're getting this thing, you're getting 10,000, not just one, but you got one here, you're getting 10,000 of this, more or less at the same price. So we're going to keep the price more or less constant. You're getting 10,000, so you got a 1 to 10,000 growth in 30 years. And then you jump, let's go ahead and jump to 2010, 2011 time frame, and now you're looking at 2 times 10 to the 9. So you just jumped again for the next 30 years. So every 30 years, it roughly goes from 1 times 10 to the 4, then roughly is another multiplication by 10 to the 5 for this. And then when you think that might be at the end of it, but you're looking at 2017 and you find out the number of transistors in a device in 2017, you're looking at things that you have 221, I think NVIDIA, a company called NVIDIA, most of you know who they are. They're kind of a graphics manufacturers for gaming and things like that. NVIDIA's GV100 has 21 billion, 21 times 10 to the 9 transistors in it. So you can kind of see the growth of this continuing to go on as Gordon Moore or Moore's law states. The number of transistors pretty consistently have doubled every 18 to 24 months. And they seem like they may continue to do that as the time goes forward, although right now we are not quite sure, the industry is not quite sure how that could continue to do that. Okay, so that's a little bit of the trend. So what we are saying, we are getting more transistors for the same space that we have. And then over the time, we've also discovered something that is pretty important to us, and that is a technology called CMOS, which stands for complementary metal oxide semiconductor. So C, complementary metal oxide semiconductor. And really the value that this has to do with the fact that it uses minimal, or almost we can say no power, minimal power when not switching. So when you build a system using CMOS, as long as you're not changing your state, this would use minimal, actually we can almost say no power, because it's going to be in the picowatt, less than 10 to the minus 12 watt type power usage when not switching. And so that's it. Why is that a big deal? Well, that is a big deal, especially if you start looking at processors that have 21 times 10 to the 9 transistors in them, and these usually are per 0.5 inches. So it's not a lot of space. You got a lot of transistors in a very little space, 0.5 inches. Now, if you think about if you even use 1 microwatt, it'll be a huge amount of power. It will burn that chip in no time. So power consumption is a big issue, and is one of the major limiting factor for how many transistors we can cram in there. So when the CMOS came along, that really opened the door for us being able to cram or jam a whole lot of transistors in a small space without necessarily burning a hole through the floor. Even though processors get hot, they are nowhere near what would have happened if you didn't have the CMOS and every transistor was consuming a microamp. In this case, only the transistors you're using consume power. So that's a pretty big important. Another trend, maybe not as important, is that as you were looking around here in time back, the main CPU was the one that was demanding more and more processors. As we're starting to look into the future, the CPUs have more or less stabilized what they'll consume, but what has happened is that we are seeing these what they call GPU, graphical processing unit. These are the one that render graphics for us, because we are getting into more simulation of real life and real color and all of those kinds of stuff, and motion. We need a lot more power. And actually, as a matter of fact, The largest number of transistor on a chip in 2010 and in 2012 were in NVIDIA products, and such that I think so so for example, the GV100 is a graphical processor unit. So it's basically a graphic cards processor, and so that's one of the changes. We are expecting the computer user interface to be much more real-like, and that's where a lot of the power is being consumed, as opposed to back-end processing and things of like that nature. Okay, so we talked about kind of the Gordon-Moore's law. We talked about the CMOS. Those are two biggies that have impacted us. As long as we are talking about the power consumption, the equation, if you want to have the equation for you, the power in watts, it's going to be equal to in the CMOS world, it's equal to the capacitive load times whatever voltage you're running at. Computers used to run at 5 volt. We've dropped that to 1.5 volts. A lot of computers nowadays run at 1.5 volt. Voltage squared times the frequency that we are running the chip at. So the higher the frequency, the higher the voltage, the higher number of chips connected to each other, you're going to have more power consumption. And by far nowadays, in addition to the real estate and ability to be able to make transistors smaller, the power consumption is a major issue. Okay. So now the next question is, what are some of the trends that are happening into the future? As far as the computer design trends are concerned, things are going to get smaller. That's just given. Everything is going to get smaller, and then it's going to be faster too. So we're going to increase the frequency, and we're going to make it smaller. That is the push. The other one is, because we're worried about the power, we're going to try to look for ways of using lower voltage to reduce the power. So lowering the voltage is something that's happening. We've already seen us going from 5 volt to 3.7 volt down to some system as 1.5 volts. I don't know where the end of this is, but that seems to be the process. We are already into nanotechnology. Things are getting smaller, as we say, so we are in nanotechnology, which basically means most of our measurements are in the 10 to the minus 9 meters. As a matter of fact, a transistor is in the range of 5 to 15 nanometer in size. So nanotechnology is a reality. It's happening. We are starting to do a lot more multi-core and parallel processing to get more power, instead of trying to build one giant system. Okay, and then of course the other thing that is happening, and we've seen it over the years, and even folks, you may have seen this trend, is that our data buses, the size of each data transfer, is going from being at 32 bits. So we used to have computers we called 32-bit computer because each data transfer for 32-bit. That has just gone to 64 very recently, and there's a possibility that would go to 128-bit as a default system size, although that may be a little while. Not sure if there is any future in anything bigger than that, but we will have to wait and see. There are a number of other kind of things happening, but those are a little bit farther out, or we're just quite not sure how it's going to play out. The use of biological computers, it's something that we should be. It's in the works. There are a lot of researchers spending a lot of time talking about, and then photon computers based on photonics as well is being talked about. Although that's been around for a while and hasn't really produced anything, but you never know. Okay, so these are some of the trends in hardware that are happening. There's many trends in software, because we have the ability and the capability to do a lot more complex manipulations, algorithms, and also we can store a huge amount of data nowadays. The memories are cheaper, the hard drives are cheaper. Artificial intelligence is really a big push that is happening. You hear it in the news when it's applied to more sexy things such as driverless car and all that, but every aspect of our life is controlled by AI. Google has been applying AI forever. If you ever buy anything on Amazon, you've been guided by AI. If Amazon and many other places, we have that going. Now, a side effect that is happening is because more of our life is online, but there's more value that is being transacted online, we are sort of having a security issue. So that's another area of growth as comes with a computer, is security. So that's basically kind of the trends of what is big, what is happening over time. Some of the things that have been continuously happening and they're going to continue to happen, of course, is more and more computer in every aspect of our life, more of AI happening in more parts of our life, and and then over time, devices starting to talk to each other without the human being involved, and taking that inaccuracy and efficiency out of it, which in all of those cases, everything that we've set up here from hardware and software becomes even more important. That brings us to the end of kind of the trends and the historical perspective and as it relates to computer systems.